The Webb Space Telescope is going to be a game-changing telescope. Not just the successor to Hubble, but so much more. The presentation has 4 parts: how Webb came to be, why study infrared light, let's explore the universe with Webb, and all about the telescope itself. Now, how Webb came to be. Who was James Webb? James Webb was the second administrator of NASA. He oversaw the Mercury program, the Gemini program, and the Apollo program. But what makes him most well known is his insistence that NASA have a strong science program, not just before military. And it's because of him that NASA does a lot of the science that they do. Here is a picture of the Hubble Space Telescope. It orbits Earth 1 revolution every 90 minutes. James Webb is going to be bigger and with more capabilities. This is a picture that was taken by Hubble. Hubble stared at a blank field, a void, for a few days and found that instead of nothing, there were thousands of galaxies there. But with all those galaxies, none of them were primordial. None of them were the first galaxies. And scientists realized that to see the very first galaxies, they would need a different instrument. Now we're on why study infrared light. Here are 2 familiar subjects taken with visible light. On the left are some meerkats, and on the right is a freshwater crocodile. The meerkats are warm-blooded, and so they glow in infrared. You can see the picture on the left. Glows most where they are warmest. On the outside, you can see from the eyes glow. The freshwater crocodile is cold-blooded. It doesn't glow so much. But you can see it glows a little bit, and that shows that it just came out of warm water. Now, to look at space things. On the left is the Eagle Nebula. They call these the pillars of creation, taken with visible light. And you can see, because of the dust and the gas, you can't see the stars inside of them. The visible light cannot reach the telescope. Near infrared light in the middle lets starlight shine through. I'm going to start out with the very early universe, and this is kind of a technical picture: cosmic reionization. At the very beginning, after the Big Bang, which happened 13.8 billion years ago, all the light was trapped with all of that gas. But over time, the universe grew, and as it became bigger, electrons combined with their atomic nuclei, and it made a neutral gas. But once the atoms started to reionize and the electrons left it, the gas got hot enough that light could escape. We cannot see with light all the way back to the Big Bang, but we should be able to see the first galaxies forming with James Webb. At the very beginning, you see that little red thing, which remember was originally blue, and you can go through all of them until we come to a modern galaxy on the left. Webb should also be able to look at black holes near and far. In our Milky Way galaxy, Webb will peer through all of the dust to study the center of our galaxy. In nearby galaxies, Webb will take high-resolution data to learn about the temperatures, speeds, and compositions of the material at their centers. Besides galaxies, Webb will look at stars. Visible light on the left shows how scorching radiation and fast winds from super hot new stars are shaping and compressing the pillar, causing new stars to form. But as more stars form, they're unseen in this dusty, towering peaks. The infrared light reveals the stars behind the gaseous, dusty veil of the nebula. And Webb will also help us to detect molecules in star-forming regions. Because it does spectra, not just images, it can help us see the gas and determine what the gas is made up of. And Webb will take infrared images and use that spectroscopy to discover what is the composition of objects and materials in detail in nearby galaxies. It also is going to look at our solar system planets. This is the infrared on Jupiter. And so it's going to study Jupiter, Saturn, Uranus, Neptune, and distant things. It can't look at the Sun, Earth, Mars, Jupiter, or Mercury. They're just too warm for Webb's sensitive infrared. And infrared also helps us find distant planets. They've blocked the light from the star, and it's just a little point there. But you can see the 5 planets that are orbiting it in infrared light. We'll also be able to decode the atmospheres of those planets. We can see what elements are in stars and nebulae, but we can see what's in planets' atmospheres. This is a picture of the Earth and shows you what is seen in the infrared light on Earth. Well, we're ready for all about the telescope. To me, this is the most exciting part. It's a feat of engineering. There are so many new and powerful technologies that make Webb's ambitious science goals possible. And Webb is going to be the most sophisticated and complex space telescope ever created. Webb is a collection of movable parts that have been designed to fold into a compact formation, because Webb is bigger than the rocket that is going to launch it. Since Webb's mirror needs to be folded to fit, its engineers ensured its 18 mirror segments can be adjusted to form a single perfect focus. Webb's sun shield is going to fold to fit, and then once it's deployed, it's the size of a tennis court, and it needs 139 tiny mechanical motors called actuators to unfold and stretch the 5-layer membrane. And here we can see Hubble versus Webb and its size. Webb has a 21.7 foot diameter primary mirror. Its mirror also needs to be stable at very cold temperatures, approximately minus 390 degrees Fahrenheit. And so it's made of beryllium, which is 6 times stronger than steel. Now, each segment is coated in a very thin layer of gold. Gold was selected because it is the best reflector of infrared light. Now, Webb has 5 science instruments, and there they are mentioned there. They are interconnected. The ones for Hubble are all separate, and one can be serviced without the others. But Webb doesn't have that option, so all of them are integrated together. And here is a little bit more about the instruments. Near Spec is going to do spectrographs in near infrared. Near Cis is the imager, the near infrared picture taker, and also has a slitless spectrograph. Near Cam also is a camera, and MIRI is the only mid-infrared instrument and will look a little bit longer wavelengths. So light is split up with the various instruments. Usually we take images and graphs, which a lot of the instruments aren't as flashy as images, and they're more boring. So even though a lot of scientific instruments take them, they are behind the scenes of some of our most intriguing headlines in astronomy. And so they spread out light and let you see individual wavelengths, which can be measured, and the result is known as a spectrum. And by looking at the resulting pictures or properties, by looking at the resulting patterns of brightness, Webb has different types of spectrographs, each designed for a different purpose. So where is Webb going to orbit? You can see here the Earth and Moon by comparison, and Earth's orbit. Webb's orbit will be at Lagrange 2 and much further away than the Moon. It says here 930,000 miles from Earth, so not quite a million, but pretty close. And it will be on the far side of the Sun, so it won't be damaged by ever looking at the Sun. So there is a sun shield sitting below the telescope. It's made out of 5 layers, all very thin. And the objects that don't have to be cold, such as the navigation instruments, the antennas where it communicates with Earth, the computer, gyroscopes, they are all on the sunlit side. And behind the sun shield are the instruments and things that need to be kept cold. It's going to take about a month for Webb to unfold, prepare, and be able to do science. There is a lot of very carefully choreographed sequence that Webb is going to follow. And this particular video shows you the sequence. This video shows the deployment sequence, so I wanted to show it to you.
As the sun rises over the Guiana Space Center, the team conducts final checks on the health and status of the Ariane 5 rocket and its payload. The James Webb Space Telescope, NASA's #1 science priority. The Webb telescope is designed to look back to a time when stars and galaxies were first forming, over 13.5 billion years ago. With its revolutionary design and capabilities, the Webb Telescope is about to unleash a new dawn of discovery.
À tous de vidéo, attention pour le décompte final. 10, 9, 8.
Seconds before liftoff, the Ariane 5's liquid-fueled engine comes to full power, followed by the ignition of the two solid rockets. We have liftoff. The Webb Telescope is finally on its way, the result of years of study and development by thousands of team members in the United States, Canada, and Europe. Webb's spacecraft ascends nearly vertically through the heavy lower atmosphere of Earth. As the rocket reaches maximum acceleration, the spent solid rocket motors are jettisoned safely into the Atlantic Ocean. Reaching the upper atmosphere where protection is no longer needed, the payload fairing is jettisoned and falls away. Accelerating through the atmosphere, the Ariane 5 rocket's first stage expends its fuel and shuts down. The empty first stage then separates from the upper stage. After first stage separation and before second stage ignition, the Webb Telescope has a slightly downward trajectory as it speeds over the Atlantic Ocean. The upper stage motor ignites and the ascent to L2 resumes, never again to be interrupted. The exposed telescope is delicate and must be protected from the sun's fierce heat. To avoid overheating and damage, a carefully designed series of oscillations are performed that provide the necessary protection. Near the end of powered flight, the roll program stops and the launcher then assumes the proper attitude for separation. After separation from the Ariane upper stage, the Webb Telescope continues its journey to L2 under its own power, taking the next step to its final orbital station 1 million miles from Earth. The Webb Telescope is about to unleash a new dawn of discovery. The Webb Telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit, and the larger orbit is the geosynchronous orbit where most telecommunications satellites are located. The solar array is Webb's first deployment. When completed, all of Webb's electrical power needs are satisfied by the solar array for the remainder of the mission. The onboard control system continually monitors and updates the attitude to ensure power generation and thermal safety. To preserve the cleanliness of the mirrors, thrusters are located only on the sunlit side of the observatory. The trajectory is designed without employing a retrofire, which necessitates pointing the delicate telescope at the sun. If course corrections are needed, these velocity additions must be done early in the flight to most efficiently use the mission's limited precious fuel. After completing mid-course corrections, the Webb Telescope passes the orbit of the Moon. Webb's initial transformation is the deployment of the sunshield pallets. tower separating the telescope and instruments from the spacecraft and sunshield is next. Next, the aft flap deploys. This is key to managing momentum buildup and fuel consumption. This structure helps to balance the pressure from the sun's light on the Webb telescope around its center of mass. After the sunshield pallets reach their final positions, the membrane launch restraints are released. These have kept the sunshield membrane safely in place from final stowage at the Northrop Grumman facility in California through shipment and launch. The sunshield protective covers roll back, permitting membrane deployment. The covers over the core region release next. Then the mid-booms extend and the sunshield assumes its hexagonal tennis court-sized shape. It is now time to tension the sunshield membranes, each thinner than a human hair, pulling each of the uniquely sized and shaped layers to their optimal position. When deployed, the sunshield allows the telescope to cool to 385 degrees Fahrenheit below zero, cold enough to liquefy air, while the layer closest to the sun is almost 190 degrees Fahrenheit above zero, nearly the boiling point of water. It's of almost 600 degrees. Truly fire and ice. Once in the shadow of the deployed sunshield, the telescope and instruments continue cooling down to their final operational cryogenic temperatures. At the completion of membrane tensioning, the secondary mirror deploys into position and is latched rigidly in place. The aft deployable radiator releases and springs into position, allowing the instruments to radiate their waste heat directly into space and away from the telescope. Disposing of excess heat is crucial to the mission so that it does not overwhelm the faint infrared signals to be collected from the cosmos. The cord-fold wings deploy and latch in place, completing the major deployments of the largest telescope in space. As the Webb telescope continues out to its operational orbit around the Sun-Earth L2, the observatory continues to cool down to its final cryogenic temperature state. A trajectory correction applied 29 days after launch puts the Webb telescope into its halo orbit, a key part of the mission design. The Sun-Earth L2 point is where Webb's orbit around the Sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of the Earth and all eclipses. Additionally, the Sun, Earth, and Moon, the brightest objects in the sky, are hidden by the deployed sunshield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery. Once the mirrors and detectors are sufficiently cold, the wavefront sensing and control operations can begin. This sophisticated multi-step operation's ultimate goal is to position each of the Webb telescope's movable mirrors into their correct final positions and orientations. Once the mirrors are aligned, the mission team will continue checking out the science instruments, preparing them for operations. Commissioning is completed about 160 days after launch, and the science mission is ready to begin. This brings to fruition the work of the thousands of members of the Webb team from the United States of America, Canada, and Europe. Astronomers from all over the world can now use this facility to study the universe. NASA's James Webb Space Telescope is a game changer, Discoveries made by this observatory will rewrite textbooks, inspiring the next generation of future engineers and scientists. This revolutionary tool will provide an unprecedented view into the birth of the first stars and galaxies, unleashing a new dawn of discovery.
Well, I hope that you enjoyed that video as much as I did. It really is a carefully choreographed deployment. And now I want to tell you about the instruments that are on Webb. The instruments are all on the Integrated Science Instrument Module. They are not separate. This shows Webb's structures, and Webb has to be stable between a gradient of 400 degrees Fahrenheit between where it was assembled and the coldness of space where it has to be. We talked to Webb from the Deep Space Telescope network. Webb communicates with its antenna to one of the Deep Space Network telescopes, Goldstone, California, Madrid, Spain, Australia, and from there the signals are beamed to Baltimore, Maryland, where the Space Telescope Science Institute is. Webb is going to discover, as I've mentioned before, things about the early universe, the first galaxies over time and their black holes, the star life cycle, and exoplanets, other planets in other solar systems. Webb has already done a number of technological innovations. The cryocooler, the micro shutters, the backplane, all of those needed to be made for Webb and are used on Earth. The sun shield, it has to be stable for a huge temperature differential, 380 degrees on one side and about 40 degrees Kelvin on the other. If you think about it as a sunscreen, it would have SPF 1 million. The spacecraft element is, and now the launch. The launch has been delayed a number of times, and right now it is set to launch on December 18th from French Guiana. The launch was delayed both due to COVID and also with the Ariane 5 rocket booster. There were a number of failed missions from the European Space Agency. And remember, it's going almost 1 million miles to its destination. Very exciting. If you have questions, this is pre-recorded, so you won't be able to ask questions live, but you can type them in the comments, and I love questions. You could also email me at my email address, which is cholmberg, CHOLMBERG, at chmuseums, plural, .org. And thank you for watching.